Okay, all right, let's get started. 4, 5, 6, 7, 8. So we got 17, 18. What's that? 19. 19 out of 35. So, again, I'm not mad at the folks that are here. It's like, where's everybody else? So, I did hear back from a couple folks that missed that one day, and everybody seemed to have pretty reasonable excuses. I say excuses, I mean, you had some pretty good reasons. But I only heard back from like 4 students. I was like, well, what about the other 8 or 9 or 10? So, just saying. All right. Hey, how's it going? Hi. Hey, what's up? Hey. No. Hey, what's up? All right. Hey, how's it going? How's it going, man? How's it going? All right. Couple quick announcements. The 3rd minute submission is due on Wednesday. I haven't set that up yet on Blackboard, but I'll do that after class. I did want to give everybody a heads up on a current RFI that I've got right now, because what I was worried about was I didn't want to get like 7 RFIs that are all asking the same thing. Okay, so I've got an RFI right now. My plan is to produce an official response either hopefully today, but worst case scenario, I'll have an official response by next class. But the 4 questions that were asked, I've got answers on 2 of them right now. So the first question that they asked was about lighting. Is there any lighting requirements on the bridge? And the answer was no, other than making sure that you're using reflective paint and any reflective devices, stickers, or the embedded things in the pavement to reflect light. No lighting is necessary on this bridge. So you really don't need to consider anything from a load standpoint. Second question was speed limit. We're going to go 55 miles an hour. Okay. The third question was on roadway curvature for shipping, and while the question wasn't directly worded this way, I'm getting the feeling what you're asking about was what's the maximum piece you can ship. Is that basically what you're asking? Okay, I'm going to think about that one for a little bit, because if I give a number, that's going to affect every group, okay? And it's going to affect, not only that, but it's going to affect every group differently. So to give you an example, where's my group 5 folks? So you all have like a 65-foot span. I'm going to tell you right now, whatever answer I give, it's not going to affect y'all. I'll just go ahead and tell you. But here's my group 1 folks. Okay, so it's probably going to have the chance to affect you all the most. So what answer I give and how I do that, I want to think about that, because if I just give a number, so let me think about that for a little bit. The 4th question I got was about a video. Is there a video? Is there something that I can provide that will help you with the bridge construction, like so you can see a bridge built from start to finish? The answer is yes, I have one. I have a link, and I'm going to provide that soon. I want to give you a couple disclaimers on it. The video that I'm thinking of giving you is part of a workshop that was done at the World Steel Bridge Symposium. I was one of 3 presenters that presented that day, and I was there and I watched this presentation. It was really good. It was from a county engineer in Ohio, and his presentation was basically on how to build a bridge in 30 days, start to finish. So, hey, how's it going? Hi. It was on how to build a bridge in 30 days. Now, so it's a pretty good overview of the process from start to finish. If I send you the link, the actual video is like 3 hours long, because it's either 3 hours long or an hour and a half, I don't remember. It's really, really long, and you only need to worry about like 10 minutes at the end. So I'll try and send you the link, and I'll say, okay, just watch these 10 minutes and you're good. The only other thing I'll mention about it is I'd say if you watch this video and you ask, does this video represent modern, normal, everyday bridge construction practices? And I would say, for the most part, hey, how's it going? I would say for the most part, and when I say the most part, I'd say like 85, 90%. There are a couple things that this engineer does that's a little unique. He's a county engineer, and so in this particular project, he was using mostly his own internal funds. So when that in that state, in that environment, he was given a little bit of freedom. I mean, he obviously had to, design a safe bridge and all of that, but he was given a little bit of more flexibility on how to build the bridge and some construction techniques. So he did some things a little differently. When I send you the link, I'll try and highlight those things. So one particular thing that I'm thinking of is normally in bridge construction practices, when you lay the formwork, you lay the formwork out in pieces. Okay, so what I mean by that is you have girder 1, girder 2, girder 3, girder 4. You're laying individual pieces of formwork between each girder. So it's separate. Okay, whereas what this engineer did, he did it a little differently. He just laid a single strip along all of the girders. Okay, and so his construction practice was actually very similar to what they do in buildings. How many of y'all have seen the pharmacy building being built out on Howard Greer? So what they do in building construction is they just lay the formwork all along the beams, and when they weld the shear studs, they weld the shear studs through the pan. So you have the beam, the pan, and the stud, and they just weld it all together. Okay, and that's what they do that in buildings all day, every day, but in bridges they kind of don't. There's a perception, and I say perception, bless you, but there's a perception that, bless you, that if you weld studs in that fashion that you get a reduced fatigue capacity. I'm not so convinced that that's the case, but and this engineer wasn't either. But I just wanted to throw that out there because if you pull up, just images of bridge construction, you'll never see a bridge built like that. And I just wanted to give you a heads up. But the video is short and it's to the point. So, any other questions? Yes.
So I feel like I know the answer to this, but
sure.
Maybe more in detail. So, for our bridge, 110 foot long.
Yes.
We know that, I assume that it's going to be very difficult to get a 110 foot long steel beam to be manufactured. Is that correct?
That's pretty long, but that doesn't mean you can't use steel.
Right. Well, that's what I'm saying. So my next question leads into the fact of, okay, so what is our length? What length should we assume our girders are going to be to, and connection-wise? Are we getting into the connection-wise of like how we're going to connect them?
Okay, all right. Let me give you a little bit more general answer, but I think I'll address what you're talking about. Let's live in reality for a little bit. Okay, let's say that you have a 110-foot bridge, and let's say I answer question number 3, and I say that the maximum shipping length, like a piece, can be no longer than 70 feet. Does that mean that the bridge just can't be built? Well, of course not. You can if we're talking about, let's say, a steel girder, you can ship the girder in pieces. So you could have a 70-foot piece and a 40-foot piece, or a 70-foot piece and two 20-foot pieces, whatever. I'd probably just do 70 and 40. And then what you'd have to do is splice them together. Now, splice design is tough. I'm just going to tell you right now. The facts are, I would argue very few engineers design splices correctly. What ends up happening is, what has happened for a long time is structural engineers will take a look at a splice and they'll see all these moments and shears all acting at this one point, and they'll just say, you know what? This is what we're going to do. Billy, we're just going to bolt the hell out of this thing. And we're not going to do that in here. Okay? If you have to deal with a splice, I've got some tools that'll make your life a lot easier, okay? Because splice design is not hard, it's just long. It's a very long process because you think, okay, you're bolting the flanges together, you're bolting the webs together, you're bolting the other flange together, so you've got, bolts and double shear, and you've got slip critical, you've got block shear, you folks now know what I'm talking about a little bit. You've got a lot of different limit states that you got to check. And so it just takes a while. And that's just the facts. Fortunately, I've got some stuff that'll make your life a little easier in that regard. But in order to get there, one of the things you will need are some accurate moments and shears. You'll need, so you'll have the beam at that particular point. What are the moments? What are the shears from end to end? And how you analyze that, you need those exact values. So long story short, that's a final design phase test, not an initial design phase test. I would like to see you maybe throw some estimates together, but I have no issue if you're literally just driving down the road and say, well, I saw a 110-foot bridge and that was a splice, and so I just went with that, because it's going to be rough, and I understand that. So, but during the final design phase, we'll refine that a bit. Don't worry.
I think our main concern is dealing with when we're looking at just our alternative space. Knowing how much we're going to be spending in terms of steel. We know that the moments are different, so we're going to have different size flanges, flickers.
Well, let me say this. Let me say a couple things. In the end, a spliced girder should act just the same as a solid girder, a prismatic girder. So, and that's generally how you design a splice. Okay. So I don't want you right now to consider the concept of splices being like, well, now it's going to change how our girder design is from start to finish. That's not the case. Just design the girder like you would any day of the week. And if you have to splice, it's something we can handle at the end. Okay?
So for our alternative space, would it be okay to go ahead and say, like, theoretically, we would have 110 foot, like, or whatever the week is. Would that be okay to design, like, the cost estimate?
Not if, so let me clarify. Not if your shipping constraints are going to give you a problem. Okay? If they are going to give you a problem, I don't want you to design a splice. That's not what I'm saying. Okay? What I am saying is this. Okay? I don't care if you make up a number, or if you, like I said, if you just drive down the road and go, there's a splice, I'm going to take a picture of it, and that's how many bolts I'm going to go with. I have no problem with that at all. But here's my point. If you have a splice, like let's say you have one, okay, then you know that I'm not going to pick one girder up. I'm going to have to pick this piece, and I'm going to have to connect them together. Okay, and so let's just make up a number. Let's say it's 80 bolts. Okay, so now the cost estimate changed. It went from just lifting one girder in place and being done to lifting two girders in place and connecting 80 bolts in the field. So if I give you just a number, 80 bolts, you should be able to determine the cost, you should be able to determine the time, the labor, etc. Can that number change from 80 at the preliminary phase to 96 at the end? Yeah, I don't have a problem with that. But I do want you to account for it if it becomes a problem. But that shouldn't be a labor-intensive issue. It's not like it takes 150 hours to add up some bolts. But I don't want to see a scenario where you got a 125-foot bridge and I told you the shipping limit was 80 feet and I don't see a splice in there at all. That I don't want to see. Does that sort of answer your question?
So would that be too grand?
It's a good question. That's a good question. It depends on your construction method. You could, that's a great question. You could have a crane over here, crane over there, lift, splice. You could, so let's say the bridge is going to go from here to here. You could connect the girders over here and lift the connected girder to the side. Whatever makes the most sense. What's your span? Okay. I know, which is why I got to think about it. That doesn't mean I don't want you to do the cost estimate. But it makes your alternative selection a lot easier, hence why I got to put some thinking into what I want to do.
So you were saying that if you did go with the 70 foot bridge we could ship, would we not, like, it would affect the shear at the moment where it's being, right? So
Where the connection is what you're saying. Well,
should we not try to make that connection like more of a number? So like, say it's 60 foot and 50 foot or something?
That's a great question. That's a great question. So you're talking about putting the splice in the middle of the bridge. Is that what you're saying?
Yeah, or not, maybe not dead in the center, but more offset, or less offset than, having an 80-foot section and a 20-foot section.
That's a great question. The answer is absolutely not, okay? And here's why. Splice design is generally geared towards developing the full moment capacity of the flanges and the full shear capacity of the webs. However, obviously moment demand and shear demand taken into account. Here's the facts. If you put a splice right smack dab in the middle of the bridge, that is going to be the biggest damn splice you've ever seen. You're going to have buku bolts and plates all over the place. Whereas if you move that splice closer to the end, it's going to decrease, the size of your splice is going to decrease quite a bit. Let me show you something. I can't, the easiest way to do this is to just draw it, okay? So let me show you something. Let's say, for the sake of discussion, actually, let's do this on the page. Let's say, for the sake of discussion, that I had a two-span bridge, okay? So I've got a bridge that goes like this, and I have, let's say, an abutment, and I've got a pier right there, okay? Now, let's say, for the sake of discussion, let's put some numbers on this, okay? Let's say that this is 100 feet, and this is 100 feet, okay? I'm going to tell you right now, there is no way that's coming in a single piece. No way, okay? So the question is, where do you put a splice, okay? Now, let's say, for the sake of discussion, that I'm going to have 3 pieces, okay? If you were to tell me that you think it's a good idea to put a splice right there, I'm going to ask you to stick your hand out. So I'm going to do that, okay? That point right there is the absolute worst place ever to put a splice, because at that particular point, you have literally the highest shears and the highest moments. Worst place ever. In fact, in design mode, a lot of attention's got to be placed right there because there's a lot going on, okay? So the question is, where do you place the splice, okay? I propose that you place the splice about right here and about right here, okay? Where this distance is something like 20 feet. Okay, about 20 feet. And you're like, where the hell did you come up with that? Are you just making stuff up? No, I'm not making stuff up. Let me show you. Here's why. Okay, if you look at a beam that's like this, pop quiz, what's the deal? Determinate, indeterminate, what's the deal? Oh, now, come on. What's that? I guess with confidence, with feeling. There we go. To what degree? There we go. Remember? You have 1, 2, 3, 4 reactions, 3 equations of equilibrium. Oh, you're looking at me cloudy. See this? This is my heart breaking right here. No. It's not Mortal Kombat or something. All right. Here's the reason why I picked those points. Okay? If you look at the moment diagram, for a section that looks like that, what happens is you end up getting like a little bit of smiley face and then frowny face and then smiley face. And so where you want to put the splice is right there, where there's no moment, okay? Now, are you going to get 0 shear there? No, that's not going to happen. If you look at the shear diagram looks something like this. So it goes up, it goes down, it goes up, it goes down, and it goes back up. And so you are going to get some shear there. It's unavoidable. But you're going to get a lot less bending moment. And so you really want to, in this instance, you would put your splice where there's no bending moment. Or you do your best to, okay? All right. In a simply supported bridge, however, that's impossible. You can't do that, okay? So because in a simply supported bridge, you know, here's your moment diagram, looks like that. There is no instance of zero bending moment. There's no instance where the bending moment crosses the axis except at the support. So you're not going to put a splice at the support. That doesn't make any sense, right? So the point is to try and hug it over to one end as closely as possible, but that makes sense.
That's what I'm asking. Is there like a happy medium? Like, how you told me like an 80-foot piece and a 10-foot piece like that?
Probably not. If you had like a 100-foot bridge, I might go with something like 80 and 20 or 70 and 30. But I would also just try and exploit my shipping requirements as much as possible. So, you know, for instance, if I had a maximum shipping limit of 70, then I go 70 and 30. You know, I feel like you had somebody over here had a question.
So you want it as close to the edge of just your lane, you're not really worried about shear at all?
Oh no, I mean you have to design for sure.
I know you have to account for it, but that's not what is like your connection.
More moment's going to beef up your splice something fierce. That's the case. So what ends up happening is this. If you want a real simple way of looking at it, so here's what a splice looks like. So you have, you know, an I-beam here, right? And then you want to connect that with another I-beam here. All right, and for the sake of discussion, I'm going to say that the I-beam on the right has thicker flanges. Let's just, for the sake of discussion. Okay, so what's going to happen is this. So the first thing that you're going to do is you're going to place a plate, something like that. Oh, you know, there's going to be a plate on the front and a plate on the back. Okay, and you're going to have bolts, you know, like something like this, something like this. Okay, and those bolts are primarily going to be designed to withstand the shear. Okay, there's a little bit more to it than that, but if you want a simple way of thinking about it, shear's 200 kips. Each bolt can hold up 20. How many do you need? Something like that. And so you're going to follow bolt spacing and layout requirements, and you're going to lay that out accordingly. Okay, but you're also going to have a series of plates up top and up top, and then you're going to have bolts going through to withstand the moment. Okay? Now, what happens when you have one flange thicker than another? You put in a filler plate. What I'm saying is more moment makes these things get huge real quick. Well, no, because a coped beam, that's a good question, but a coped beam is when you have beam A and beam B going like this. But that's not what's happening. Here you've got like a beam, and you're trying to splice them together like this. So coping the beam would actually make the splice even more difficult because you need that flange there to bolt to it. And so a coped beam, you're cutting that flange out. But that's fine if you've got beam A framing into beam B. But in that instance, there's no moment to consider. All you're looking at is trying to transfer the shear. So that's why that flange doesn't really matter. Wait. No, I think I see what you're saying, and the answer is no. One thing, though, whenever you're designing girders and you've got girder A and girder B, and the girders are different sizes, one of the things you'll always want to maintain is the web depth. You want the web depth to be the same so that the webs line up. Now, it's okay if, you know, let's say we get over here. Let's say we get over here and the shears get really, really high, so we need a thicker web. Thicker web's fine. Deeper web, not fine. You want to use the same depth on the web across the structure, but you can change the thickness, but don't change the depth. And I'd say that's true really for any system just from a putting things together standpoint. So I don't think that really matters if we're talking about steel or concrete. I don't really think that matters. Did I answer your question though? Because I think maybe did I?
No, I understand a little bit more now.
Okay. Anything else? This is good stuff. Yes.
So I was kind of thinking, like, when I was talking about 14, maybe removing the flange on the beam with the smaller flanges, like removing the flange on the top and the bottom for so long, and then cut out the web with the bigger flanges. I would say you could like, you see what I'm saying?
You mean like a puzzle piece almost?
So like so instead of like having all that moment. The connections are staggered. Yeah. Is that something?
Well, I mean, I guess it's possible, but I don't really know. Like, I don't really know what the benefit would be from a capacity standpoint. Here's the reason I say that. Okay, in the end, you're still going to have girder A to girder B, right? They're still going to be connected, and you're still going to need bolts to transfer that load from girder A to girder B. So I don't know if changing that detail of how those two girders come together, I don't know how that would change the number of bolts. I don't know how it would change the thickness of the two plates on either end. That's what I don't understand.
Well, can you move the flange connections closer to the edge where the moment's left? As the wedge and connect the
Okay. That's possible, but then you have a pretty significant region where the flange and the web aren't connected at all. Do you want to weld in the field? See, that's an interesting point. Pretty much every state in the country will not allow welding in the field, except for one, and that's Texas, because they're Texas. No. No, in actuality, Texas has a specialty team of folks that do this for real. Like, this is what they dedicate their careers to, is welding steel plate girders in the field. And so Texas will allow that, but nobody else will. And so you could do that if you were allowed to weld in the field. And so if we were in Texas, we might be having a different discussion. But keep in mind, if you did that, you'd also be bumping up the price because we're talking about a team of specialists. You know what I mean? But that doesn't mean it's impossible. So, sure. Yes, and that's why you have a haunch, because you're going to have, because you've got girder A that's thicker than girder B, so you need the concrete deck sufficiently raised so that it's flat. So, we've been using 2 in here. Yeah. Yeah. In fact, in instances like this, it might not be that uncommon to use something like 3.5. I mean, that just is what it is. And so the fillet thickness, now the haunch might be the same, but the fillet thickness is going to change along the girder. So you remember how when we did the dead load calcs, we said just 14 inches wide and here's the thickness along the entire span. Well, that was fine when the girder's the same. But if the thickness changes, you got to compute a weighted thickness. Like the fillet is this thick over this region, and it's this thick over this region, and it's this thick over this region. So what's the average thickness across the entire span? So you got to compute a weighted average.
But that's going to be a really small percentage, right?
Oh, you're absolutely right. You're absolutely right. But not over here when the flange is thicker. But over the splice, yeah, it's going to be really small. Now keep in mind, we've kind of accounted for the weight of the splice and the bolts because we did that in miscellaneous details. If your splice is freaking huge, maybe go with 7% instead of 5%. Maybe bump that percentage up a bit. So if you're in Pennsylvania, they'd make you count every single bolt and every single plate. Yeah. When you're designing bridges, there's Pennsylvania and there's 49 other states. So that's just... No, I mean, Pennsylvania has their own sort of way of doing things. I'm not saying it's a bad thing. Actually, a lot of their record keeping and a lot of their methodologies are worth borrowing, to be honest. So,
48.
well, no, Texas just has that one crew. So, oh goodness. All right, are there any other questions? Because I want to get at least to finishing these dead load caps. All right, so let's sort of recap what we left off with. So here was our bridge, and we've been taking this one step at a time, and we've been trying to take this cross section, and we've been trying to break down its dead load computation. So first thing I want to make sure that everybody's clear on is this. So we had the girder self-weight, we had the miscellaneous details, we had the SIP forms, the slab, the fillet, and then what we haven't done is the deck overhang. That's the one thing, the overhang taper. That's what we're missing. That's the one thing left in DC1. But for DC2 loads, we've got the barrier and the parapet, or the parapet, same thing. And DW, we have the future wearing surface. And so what I've been doing is taking each of these one step at a time. So we did the girder, which was just the unit weight times the area. Units. Pay attention to units. The miscellaneous details, we just assumed that all the cross frames, the bolts, the studs, and all that stuff, we assumed it weighed 5% of the girder weight, which is a pretty reasonable assumption. The SIP forms, we assumed that the forms themselves weighed 15 pounds per square foot. And so what we did is we said, okay, it's 15 pounds per square foot applied over a tributary width, but our tributary width in this case is basically just summing up all the lengths. So we're basically talking about the forms being applied over this blue region here, from girder to girder, from girder to girder, from girder to girder. And so that length is not 10 feet. It's 10 feet minus the flange width, because we come in a little bit here and a little bit there. And so the top flange width was 14 inches. And so the way that we did that is we said, okay, the girder spacing is 10 feet, or 120 inches. So we have 15 pounds per square foot times that width. Then we converted it to feet. Now there's 3 widths, but that's all the SIP forms on the entire bridge. So we've got to divide that by 4 because there's 4 girders. So the entire SIP form on the structure divided by 4. As for the slab, the philosophy is kind of the same. The slab is 8.5 inches thick. It's not 8 inches, it's 8.5 because we're taking the total thickness. So 8.5, convert that to feet, times 37 feet, times the unit weight of concrete, over 4 girders. So that's 982.8 pounds per foot. Now the fillet, we take the 14 inches times that thickness, which is 1 1/4, because the haunch is 2, the flange is 3/4 of an inch thick, so we're talking about the difference. So that area of concrete times 150 pounds per cubic foot, we got to do a unit conversion because we got to convert this square inches into square feet. So it's square inches to square feet. So it's 144, and so we get that. Everybody okay with this? All right. If it's okay, I'm going to erase this. Because we have, how did I do? Oh, I did that a little differently. Because we have the overhang taper. Okay, and so let me explain how the overhang taper works. Oh. Okay, so here's sort of the edge of the deck, and then if you want, what I'll say is, you know, the barrier sort of comes up there, but we're not worried about the barrier right now. Okay, and then we have the deck. It comes down. Then we have our flange and our web. And so that's our girder, okay? And so, you know, you would think that this comes down like that, right? And that's the edge. But that's not correct. Usually what happens at the end, instead of that coming down and cut like that, usually what this looks like is this. usually you have sort of a taper on there. Okay? The reason for that taper is because of the presence of overhang brackets. Let me see if I can, I don't have my keyboard, so this is going to be interesting. No, I don't want to mess deck overhang brackets. And so what we're talking about is sort of something like this, or maybe something like that. Maybe that's a little better. Okay, so what we've got here is these overhang brackets where they serve as support for the formwork on the overhang. And so usually what happens on the deck is that the overhang bracket would sort of be, it would sort of lay flush against the girder, and then it would come up like this, and then you'd have a strut coming down. And so there's a little bit of a taper to the concrete deck. And so what we've got to do is we got to figure out what's going on with that red shaded area right here. We got to figure out that way. I'm going to erase this. Okay. Now, let's see if everybody's paying attention. What is this dimension right here? 3.5 feet. Or let's put that in inches. So that's the overhang. Now, 3 feet is 36 inches, plus 6 is 42, right? Now, is that how wide the triangle is? No. How much do we have to back off the triangle? No, hold on. It's half the flange thickness, right? So if you want to do this symbolically, this dimension right here is the overhang minus half the flange thickness, right? Okay. Now, how tall is that triangle? What's that? It's 2 inches, right? Because that's the haunch. So if you want the weight of the taper, here's how we're going to do this. We're going to say the area of the taper times the unit weight of concrete times what? Let's do this. How many tapers are on the bridge? There's 2 of them, right? There's 1 on each end. All right, so if I multiplied this by 2, that would be all the tapers on the bridge. Then what do I do to that? Divide by 4. Why am I dividing by 4? Because that's the number of beams or number of girders. So now let's compute the area of the taper. So what's the area of this triangle? It's 1/2 times 42 inches minus 14 inches divided by 2 times 2 inches, right? Now that is square inches, all right? So what I'm going to do is I'm going to throw a unit conversion into there to say 1 square feet is 144 square inches. So now the area is in square feet. Fair statement? Okay. Now I'm going to multiply that times the unit weight of concrete. 150 pounds per cubic foot. Then I'm going to multiply by 2, divide by 4. I just don't want you to think that these formulas and these values are just coming out of nowhere, that there's a reason for them. And one of the thing while you're crunching numbers, keep in mind, I'm showing you how to compute loads on the bridge in question. Your bridge, your alternative might be completely different. It might not even look anything like this. But the same philosophies still apply. Now, how do you compute the unit weight of something? It's gamma times the area. That's not the unit weight, the weight per foot. It's gamma times the area. Say it again. Do I have a second on that? Okay. All right. So to summarize, help me out. We had the weight of the girder, the weight of the miscellaneous details, the weight of the SIP, the weight of the slab, the weight of the fillet, and the weight of the taper. Now I know this one's 18.2. Oh, I don't know what happened there. 18.2. Help me out with the others. What's the weight of the girder? Why do I want to say the next one's 8.3? Man, I'm good. I don't remember. I'm not that good. All right, hold on. 99.4. Now, hold on. Let me try something. 982.8. I have no idea how I remembered that. Okay, I don't know the next one. 18.2. I think that's coincidence. Everybody good? So let's sum these up. I see these engineering students without their Casio FX115 ES Plus. Okay, I know he's an RPN guy. That's fine. 1293.2. Where's your HP 48? So therefore, I propose that the DC1 load is 1.293 kips per foot. So what's going on if you're like, well, what does this mean? I have a bridge. Let's say you're group number 3. What's the span on group 3? So if you have, let's say, a 95-foot bridge, then you have a load. DC1 is 1.293. Per girder, yes. That's per girder. That's a good point. And so in girder design, that's how I would design each girder. You know, now it's dead load, and that's only one dead load. We got 2 other dead loads to consider, and then next we start talking about live loads. So now the other loads, now DC1 took forever. DC2 and DW, they're really easy. Okay? On this bridge, what's the only DC2 load? The parapet, right? And so how would we determine, let's say for the sake of discussion that we knew the weight of the parapet. How would we determine the weight on each girder? We take the weight of the parapet, multiply it by, because there's 2 parapets, and we divide by 4. So as long as you know what the weight of the parapet is, you're good. So the question becomes, how do you find the weight of the parapet? Well, it depends on the parapet that you're using and what specs you're using. Open up the West Virginia DOH standard details. It's there. Okay? So I am going to do this for DC2. We're going to assume a 500-pound per foot parapet. And that's actually pretty reasonable. If you're using a concrete jersey barrier, I mean, think about a concrete weighs 150 pounds per cubic foot. You're talking about a concrete beam that's like yay high, you know? That's pretty heavy, you know? Talking about a concrete beam that's yay high and about yay wide. So that's a pretty hefty beam. So, in fact, when you're doing live load distribution studies, you have to eliminate your parapet because your parapet is just another beam that's going to suck in load, right? See? It all comes together. So I propose that DC2 is just 500 pounds per foot times 2/4, or 250. So that's easy. Okay? As for DW, here's how DW works. Actually, let me do this. Okay. Here's how DW works. DW is the future wearing surface. So that's the overlay that we apply over and over again to the bridge over its design life. I mean, what happens if you have a bridge and it's been the same for 10, 15 years? After a while, you got to scrape that overlay off and apply a new overlay, right? So over time, that overlay is going to change. It's going to keep getting reapplied. So we need to account for that. Okay, and that's what from a load standpoint, we call that a future wearing surface. Okay? Most codes and West Virginia DOH bridge design manuals, nudge, nudge, hint, hint, wink, wink, will tell you what's a good value to assume. Okay? What we're going to do here is we're going to assume 25 PSF. Okay? So in order to determine D sub W, or DW, not D sub W, DW, this is how this is going to work. We're going to take 25 pounds per square foot. We're going to apply it over a width. And so we're going to talk about that width here in a second. And we're going to divide by 4. Okay? Now let me ask you a question. This is the future wearing surface of the road. Over what width do we think that this is going to be applied over? Say it again. 24 feet or? Well, now hold on. Do they not pave the shoulders? So here's the bridge. What width do you think we applied over? The 34, not the 37, okay? Think if you're putting asphalt or some overlay on this bridge, it's going to go from end to end, right? But it's not obviously going to go here because there's a big concrete barrier there, okay? So we're going to apply that over the total width of 34 feet. Then we divide by 4. And so what's that come out to be? Bless you. $212.5. Okay. And so if you're wondering where the application for each of these numbers are, so what we can do is we can say, all right, here's my dead loads. If you put dead load on a beam, you can determine dead load moments, dead load shears. Y'all took structural analysis, so you know how to draw a shear and moment diagram. That's the dead loads. What about the live loads? That takes some discussion, okay? And I'm not going to get into that discussion today, but what I will say is this. It begins with the wonderful world of influence lines, okay? So basically, here's how live load works, and then we're going to call it. You have a bridge, okay? So here's the bridge. It goes from here to here, and here's how wide it is. Okay? And so what we got to do is we got to figure out two things. I'm getting a phone call from Brandy. I'm going to ignore that for now. I don't have a, no. Here's my design truck. What I got to do is I got to figure out two things. Where do I put the truck along the bridge? And where do I put the truck across the bridge? Where do I put the truck along the bridge? That's where influence lines come into play. You all have done that before. Where do I put the truck from side to side? That's where a thing called live load distribution factors come into play. You haven't done that yet. We'll do that later. That's all I got.